Hello, fellow math students. I hope you're having a wonderful year so far. Today, we are going to take a look at a problem concerning fields. So let's jump right into it. The problem gave us a field, which is a Gallows field 7. For those that don't know what it is, I wrote it out there. Just as a quick recap, it's just the modulus of 7, so it's the remainder after you divide by 7. So any value divided by 7, you take the remainder, it will fall between 0 and 6, from 0 to 6. And if you add any of those terms or multiply them and divide by 7 again, you'll end up with a value inside the field, which is from 0 to 6. So that's basically how the Galois field works. Then they gave us this operation, K, and this operation is the composition of field elements. And I just wrote in red what it entails. They gave us then two operations, one for addition, one for multiplication, and they asked whether these operations turn K into a field. Now, to do this, I quickly recap just fields on the right, just so we know what exactly the conditions for a field is. And we have to show that these operations, addition and multiplication, is associative, that they commute, that the multiplication distributes over addition, that there's identity elements for both operations, and also inverses. So to do this, we are going to proceed as follows. Right, let's see. Okay, let's write down then field condition 1. So field condition 1 basically wants me to show associativity, and we're going to do it by then associating those two, and then check whether I can associate it the other way around and still get the same result. So we're going to do the brackets part first. We will have C plus E, and we will have D plus F. Then if I add that, I will get A plus C plus E, B plus D plus F. So, but because A, B, C, D, E, and F are all elements of a field, that means they will associate. So I can just very easily write it like this. So how to do that since they are elements of a field. So it's very simple then to show that in fact addition is associative. Okay, let's look at multiplication. So multiplication, let's maybe write down first the operation for multiplication since we didn't really pay too much attention to it there. It's basically the product of the first components minus the product of the second, and then we have the product of the outer plus the product of the inner. That's basically how it works. So if I do want to show associativity, I will again have to use 3 different elements of K. Okay. We will do it like that. So then, let's do the bracket part first. So if we do the bracket part first, we'll end up with, don't really have to do a bracket there. We'll end up with CE minus DF, and we will have CF plus DE. Okay, and then we'll multiply that. So if we multiply that, let's maybe make some space here. When we multiply these, we will end up with this. So again, applying the multiplicative operation. Sorry, CE minus DF minus B CF plus DE for the first component. The second component, let's scroll to the right a bit. For the second one, we'll have the outer, the product of the outer, plus the product of the inner. C, D, F. Right. So then, because A, B, C, D, E, and F are all elements of a field, I can then multiply the brackets out because multiplication do distribute over addition for the Galois field 7. Meaning, I can multiply it out and then group the terms in a different way to get the desired result. And I'm going to group the E and F terms separately. So for this one, then I'll get AC minus BD, which is just times E. Then I'll take out minus a common factor. And in this one, I'll have, it's going to be AD, and I'll end up with plus BC, which times with F. On this one, I'm going to do the same thing, group the E terms first. So I'm going to have AD plus BC, E plus, I will have then, I'm going to group the F terms, which will give me AC minus BD, F. Right, so now if I were to write this out quickly, you will see that the what you see above is actually a product of the following. So let me actually write it out so that you can actually see what I mean. It's AC minus BD, and my second component will be AD plus BC, and then that's multiplied by EF. So remember, our multiplication basically takes the product of the first minus the product of the second for our first component, which is exactly what happens here. So you'll see here that this is the product of the first and this is the product of the second. And we subtract that, okay? And then in the second part, for the second component, we multiply the outer, which is this one, and we add it to the multiplication of the inner, product of the inner. Okay, and these commute because it's elements of a field, so I can swap them around, doesn't matter. And that's why I get this, I end up with this. But now it's also easy to see that this first part is actually the multiplication of this. So the first part was actually the multiplication of A, B, and C, D, the components of that. So then I've shown already that multiplication is actually associative. I can associate two and then associate the other two and still get the same result. So for the next one, field condition 2, we have to show that it commutes. So again, we'll start off by using two elements from K. And I'm going to have A plus C, and this is going to be B plus D. So now, because A, B, C, and D are all elements, they actually do commute, so I can very easily just do this. And that will give me CD plus D. And so, very easily, that actually commutes. For the product, we're going to have to check whether that commutes. We have AB times CD. And so the product says it's going to be AC minus BD. Going to have AD plus BD. Now, again, because A, B, C, D are all elements of a field, they do commute with multiplication. So I am more than welcome to write this as DA. So this is just this. Okay. Right, so multiplication was fairly easy. For condition 3, so field condition 3, we have to show that multiplication will distribute over addition. this. So we need to show that the element that I multiply with that addition will actually distribute over the addition. So let's start by doing the bracket part first, which will then give me C plus E, D plus F. So if I applied multiplication according to the rules, I'll end up with A, C plus E minus B times D plus F. And then for my second component, it's the product of the outer plus the product of the inner, which will give me A times D plus F plus B times C plus E. Right. So now we can actually multiply this out and then yeah, and then again group it in such a way to get the desired result. So we'll group it differently. So the way we're going to group it is we want to group the A, C, and B, D together. So this is what we're going to do. We'll multiply it out, and then we're going to associate, because A, B, C, D, E, and F are all elements of a field, they do associate, so I can associate them differently. So I can do this, okay? So I can associate the AC, which was multiplied, minus the BD, so I can put them together. And then I'm going to have plus, I'm going to put together the AE minus the BF. And then here, same thing, I'm going to say it is AD plus BC, which I will associate. And then plus, I'll end up here with, yeah, I'm going to associate the others. I'm going to say it's AF plus BE. Okay, and then through the addition operation, I can very simply just separate this as follows. I'll get AC minus BD, my first component. For the second component, I'll use AD and BC again, plus AE minus BF, get AF plus BE. And as you can see, I just used the addition operation, which was given to us in the question, to split the first and second components into its additions. And then I get two different compositions, and very easily one can see, if you note that this first term is actually the product of this. So it's the first product of the first minus product of the second, which is our first component, and it's the product of the outer plus the product of the inner. And then for this other one, it's AB and EF. Right. So we have now shown that this one actually does in fact distribute. So it distributes. So the multiplication distributes over addition. That's fine then. Let's look at field condition 4, which is identity elements. Now, for addition, let me write down the elements of the field quickly. So for addition, all that we really need to show, because the addition operation is straightforward. I mean, addition is just, as we've already seen multiple times, but let's just write it out. Excuse me. Plus C, B plus D. So all that needs to show is that since K is a composition of the elements of F, and the addition is just the addition of the different components, which eventually adds elements of the field, we just have to show that each element in the field, which is this one, my Galois field, I just need to show that each element here actually does have an inverse, an identity. And we know that 0 is actually part of the field, which is an identity for every other element. So I can very easily, by composing the zeros, by composing zeros, I will then, because 0 is an additive identity, is an identity element for the elements in F, then it means A plus 0 is just going to be A, and B plus 0 is just going to be B. So 0 and 0 is my identity element. For multiplication, it's also fairly simple to show that your identity element is that. Easily show that it's first product of the first minus product of the second, and we have the product of the outer plus the product of the inner, which will eventually map back to A and B. Okay, so both has actually identity elements. Now we have to show for field condition 5 that we have an additive inverse. Okay, so if I write down the field like I did above, then I know that 1 has an inverse in 6. So 1 plus 6 is 7, and that's 0. 2 plus 5 is 7, 0. 3 plus 4 is 0. So each element actually does have an additive inverse, meaning each composition of elements where A and B are elements of F will have an inverse, an additive inverse, as shown in the field. So each one of them does have an additive inverse. A and B will both have additive inverses, and it doesn't matter which I compose, there will always be an additive inverse. For the multiplication, it will require a little bit more work. So let's multiply. Let's say my inverse for multiplication is V1 and V2. Usually this is used for vectors, but bear with me now. V1 and V2 are elements of the field. Let's write it like this. Let's say for V1, V2 elements of F, we will get A V1 minus B V2, and we'll get, we will get here, we will get A V2 plus B V1. And then basically what needs to happen is AV1 minus BV2 must be equal to 1, and AV2 plus BV1 must be equal to 0. So now I have two equations which I can solve simultaneously. So what I'm going to do is I'm going to multiply the first by A, and I'm going to multiply the second by B, and then I'm going to add the two. So I'm going to get A squared V1 minus AB V2 plus AB V2 plus B squared V1. That must be equal to A. The center terms will subtract, so I will end up, and if I solve for V, let's just solve for V, which is simple to see, will be A squared plus B squared. If I substitute that into equation 2, okay, so I'll get A B2 plus B times over A squared plus B squared, and that must be equal to 0. So if I solve for V2, I will get minus B over A squared plus B squared. So thus my inverse, my multiplicative inverse, which in this case was V1 and V2, is actually this for any elements AB, the field F. So what needs to happen now is I need to show that this inverse operation is actually only trivial solutions for Galois Field 7, because what's going to happen is if I were to say that for every element AB, every composition of elements AB, to have an inverse, then this cannot be 0 unless A equals B equals 0. So if both A and B equals 0, then I will just end up with an inverse of 0 again. But I can't have A squared plus B squared equals 0 for any other composition. So what we're going to do is we're going to take the squares, we are going to take the squares of Galois field 7. Okay, and the squares of Galois field 7 is going to be, so the square of 0 is 0, the square of 1 is going to be 1, the square of 2 is 4, the square of 4 is going to be 2, the square of 5 will eventually give me 4 again, the square of 6 will give me 1. So ultimately, oh, there's a square of 3 as well, which is 2. Sorry, let's just insert it here. So there's another 2 here. But we will have, basically we can narrow it down to, so the squares will be 0, 1, 2, 4. And interesting, for all these squares, the sum of any two of them, even if they're not distinct, so I can add 1 and 4, 2 and 4, 1 and 2, 1 and 0, 1 and 2. So if I add them, I will never get 0. So it means that none of the squares of the Galois field 7, none of those squares will eventually give me this unless, as we said, unless A equals B equals 0. So that means, so we can say thus, K is a field given the operations with F equals Galois field 7. So it works. We've shown that all the conditions hold, and even the inverse condition holds, because we have only trivial solutions for our inverse operation. All other elements that we compose will have inverses. So it works, it's not undefined. For the second question, they asked us, but what if so in the second question, they said, what if F equals Galois field 5? Now then we might have some problems, because if we do the same as we did for, let's do the inverse. So if I take the squares of Galois field 5, so we're just going to show it with the inverses. For a lot of the other conditions, it might hold, but we will see a contradiction or a problem with the inverse. So if we take the squares of Galois field 5, we'll get that is 0, 1. The square root is going to be 4. The square root of 4 is going to be 1. The square root of 3 is actually going to be 4. So it's 0, 1, just 4. The square root of 3 will again be 4. So again, I forgot about 3. So the square root for 3 is again 4. And then we have the, then we have the square root for, actually for 4, yes. So the square root for 4 was 1, sorry. Okay. So I can narrow it down to the squares of Galois field 5 is 1, 2, and 4. But these will give me problems because I can see that if I sum 1 and 4, I'll get 0. So basically what this tells me is if I were to use the composition, so my Galois field 5, let's maybe just quickly write down Galois field 5, is actually 0, 1, 2, 3, 4. So if I take the composition 1 and 2, for example, this inverse, so the inverse of 1 and 2, the inverse of this one is actually going to be, 1 over 1 plus 4, and 1 and minus 2. But this will give me 0, so thus this is going to be undefined. That's actually undefined. So K cannot be a field when Galois field is 5, because there won't be inverses that can be defined. So we can't have multiplicative inverses when the Galois field is 5. And that is that. If you have any questions regarding this problem, please leave a comment. If you have other problems maybe you'd like to pass my way, please feel free to put that in the comments as well. Thank you so much. Have a wonderful day. See you again. Bye-bye.